Hi everyone. We're going to determine alkalinity in Duck Pond and Boone Creek by titration, and again we're using a standard method that comes from this book. Alkalinity is the ability of a water sample to neutralize acid. And next week I'll try to prove to you that alkalinity is not the same as pH. Now, if a water has the ability to neutralize acid, that must mean that that water contains bases. And the most likely base present in a natural water sample that's going to neutralize acid is this bicarbonate that comes from carbonate. And if you remember from the hardness experiment last week, the main source of carbonate in natural water is limestone, which has the formula calcium carbonate. So the units for alkalinity are the same as the units for hardness: milligrams of calcium carbonate per every liter of sample. This is your experimental setup. Your titrant is going to be a very dilute solution of hydrochloric acid, 0.02 formol. And if you don't know what formol means, it means pretty much the same as molar. So in this case, 0.02 formol HCl just means 0.02 moles of HCl for every liter of solution. And we use formality for electrolytes that dissociate in solution. So again, you'll have your titrant here, which is again that dilute HCl. Every drop of your titrant will pass through a drop counter. You'll have a pH probe immersed in your sample, and you will be titrating a 100 ml aliquot of Duck Pond and Boone Creek, and you want to measure this 100 ml aliquot as precisely as possible. So you'll use a 100 ml Vol pipette or Bertha. She's a big one. And then your pH probe and your drop counter are going to be connected to these handheld vernier devices, which will allow you to see data being acquired in real time. You will be able to save your data by placing a thumb drive. I'm not sure where exactly, but you'll be able to save your data onto a thumb drive. And then we'll analyze these data next week in lab. So please do your best to bring a thumb drive with you for this experiment. Either you or your partner should bring a thumb drive to lab. The beauty of this titration is that we monitor the pH during the titration. That means we never have to worry about over-titrating. Last time when we titrated for water hardness, maybe you were worried about turning your solution too blue. Here, that's not a problem. We're going to be monitoring the pH versus volume of titrant added to create a titration curve. And let me ask you this. What do you think the initial pH of Duck Pond or Boone Creek might be? Well, historically, it's around 7. So what you're looking at here is a titration curve, and you'll be able to see these forming in real time on your vernier devices. A titration curve, again, is just a plot of pH versus volume of HCl. We started off with a roughly neutral pH, and then we titrated. We were adding acid until the pH dropped. Now, what is the endpoint of this titration? The endpoint occurs at a pH of 4.5. So once you get these data, you'll use the volume corresponding to that pH, and that's known as the equivalence volume, or V sub EQ, and you'll use that next week to calculate the alkalinity of the Duck Pond and Boone Creek samples. So in other words, when you're titrating the water samples, it doesn't matter if you go below 4.5. In fact, you want to go a little bit below a pH of 4.5. Now, if you think about our first titration determining water hardness, we titrated Duck Pond and then we did a QC and that was it. Well, this experiment is slightly different because our titrant HCl is not what we call a primary standard. A primary standard is certified to have some level of known purity, usually greater than 99.9% pure, and HCl isn't that pure. So we have to standardize our HCl. So what we're going to do is we're going to prepare a 0.1 formal solution of HCl, standardize it with reagent grade sodium carbonate, which is a primary standard. So your reagent grade sodium carbonate is going to be in your beaker this time. We'll standardize this 0.1 formal HCl, and then we'll dilute it to 0.02 formal, and that's what we'll use to titrate Duck Pond and Boone Creek. Now, this sodium carbonate needs to be dried in the oven, and when you do that, you want to put your sodium carbonate in a weighing bottle. You don't necessarily need to have the cap here. It's fine if you do. Put your weighing bottle in a beaker and then cover your beaker with a watch glass just to keep dust out. And then see the procedure for how hot the oven should be and for how long you have to dry your sodium carbonate. But I wonder what the titration curve for the standardization is going to look like. Let's talk about that. So remember, we're measuring the pH during the titration. And if you had a guess, what do you think the initial pH of this sodium carbonate would be? Well, I hope you thought that it would be basic. In this example, it was roughly 11. So let's talk about what's happening during this part of the titration. Every time you add H plus during the titration, that H plus is going to neutralize the carbonate in the sample. So at this point in the titration, every time you add H plus, it gets consumed and your solution contains a weak base and its conjugate acid, also known as a buffer. So this point in the titration is your first buffer region, but then you reach a point in the titration where you've added just enough H plus to neutralize all of the carbonate. So H plus is gone, carbonate is gone, and that extra drop of H plus that you add really drops the pH quite a bit. And that takes you to your first equivalence volume, shown here as VEQ1. But you're going to keep going. You're going to keep adding H plus, which is going to react with all of the bicarbonate produced here, shown by this reaction. And again, at this point in the titration, every time you add H plus, it gets consumed. So the solution contains a weak base and its conjugate acid, or a buffer. So this is your second buffer region. But you'll reach a point where you add just enough H plus to neutralize all of the bicarbonate. So H plus is gone, bicarbonate is gone, and that extra drop of H plus really drops the pH, taking you to the second equivalence volume shown here as VEQ2. And then you'll want to titrate a little bit beyond that equivalence volume so you see this little tail here. Now, these volumes, VEQ1 and VEQ2, will be used to determine the actual concentration of this 0.1 formyl HCl. So as you're preparing your solutions, you may ask yourself, what glassware do I use? Is it okay to use just a graduated cylinder? Or do I need the precision of volumetric glassware? Well, we need to think about the nature of these solutions. So in the procedure, you're going to be making 500 mils of 0.1 formyl HCl from a stock solution of 6 formyl HCl. So you'll want to use the equation C1 V1 equals C2 V2 to calculate V1. And then you'll do the same thing to prepare the 0.02 formyl HCl that you use to titrate Duck Pond and Boone Creek. Again, you'll use that same equation to calculate how many milliliters of 0.1 formyl HCl do I need to prepare 250 mils of 0.02 formyl. So yes, this question about what glassware do I use may come up. But let me remind you of something. 6 formyl HCl, your stock solution here, is not a primary standard. It is about 6 formyl HCl. You don't know the concentration of that 6 formyl HCl very well. You only know it to 1 sig fig. Now think about how we determine the actual concentration of the 0.1 formyl HCl. If you think about it, the actual concentration of this has nothing to do with this. Instead, the actual concentration of your 0.1 formyl depends on the titration, the standardization, in other words. It depends on VEQ1, VEQ2, and how many grams of sodium carbonate that you used in that titration. The actual concentration of the 0.1 formyl HCl depends on your standardization or your titration data and has nothing to do with this dilution factor. So this is the one time in Quant Lab if you're preparing the solution in a 500 ml flask and you dilute it over the mark, it doesn't matter because you're going to standardize it anyway. So whatever you get for V1 here or X sub 1, just use a graduated cylinder because you don't need that level of precision. The actual concentration is going to be calculated from your titration curve. But now, think about how you determine the concentration of this, the 0.02. What does this concentration depend on? It actually does depend on this dilution factor. So whatever you get for this volume here, you better use a vol pipette. So just a few reminders. Remember, the pH electrodes have a delicate glass membrane at the bottom, so be careful with them. You want to rinse this glass membrane well in between samples and buffers. You want to store it in pH 7 buffer when not in use. And your pH probe may or may not have a little fill hole here It just depends on what type of electrode you get. If you do have a fill hole, make sure it's open when you're using it, but close it during storage. Remember, when you're titrating Duck Pond and Boone Creek, you want to titrate until the pH is below 4.5. And for the standardization, you want to go beyond that second equivalence volume. So you want to see this little tail here. Remember to record your burette volumes to 2 decimal places. And don't forget to save your data. Again, hopefully you or your partner will bring a thumb drive to lab. You'll work in pairs. I will assign those pairs, and you'll be doing both Duck Pond and Boone Creek. For safety, as always, we'll be wearing goggles. The main safety hazard is this 6-formyl HCl stock solution. I would wear gloves when pouring it and try to use it sparingly. Take only what you need. The other safety concern is that the ovens are hot. And remember, hot objects look the same as cool objects. So if you see a beaker and you think that maybe it was in the oven, just, be mindful of that. It could be hot. All of your liquid waste should go into the liquid waste container, and the only solid waste you'll have will be the excess sodium carbonate, and that'll go in the solid waste container. So next week, we will go over the calculations. Please read the handout and be ready. And most importantly, please read the handout for this experiment and be ready to start titrating as soon as lab begins. Good luck. I hope you enjoy the experiment and be safe. Thank you.